Hello, everyone. Today, we're going to do a full review of AP Calculus AB and BC. So BC has pretty much the same content as AB, just a few more topics and some units, and 2 extra units. So first unit, limits. So limits, think of it, limits can be used to define instantaneous rate of change. Instantaneous rate of change is just a derivative, and as you'll see later, we'll use limits to help define what a derivative is. So for limits, just know that as the x value gets extremely close to, but not equal to, a certain x value, what y value is approached. So here I have this graph, right? On the bottom left corner. As you can see, the limit as x approaches 4 is just 5. Because as the x value gets really close to 4, the y value is 5. And on the right, I've written, this is sort of like a pre into what a derivative will be. We're going to go over the equation on the right later. But yeah, essentially know that limits are just defined, they just define what y values approach as the x value gets really close to a certain value. So continuing on limits, you can identify limits from a graph or from a table. So on this table that I have here, if you look at the values, what do you think the limit as x approaches 0.3 will be? As you can see from both sides, the y value f of x is approaching 1.0. So that's why the limit as x approaches 0.3 of this function is 1. On the right, I have this piecewise function, and as the limit as x approaches a, we can evaluate it from both sides. So the limit as x approaches a from the right side, that is just going to be a. And limit as x approaches x, I guess, from the left side, that's going to be b. So yeah, I know I included limit as x approaches a, just to note that was just a typo. It should be the limit as x approaches x here. And from the left-hand side, so the negative side, left-hand side will be negative, so you will just see the negative side. So that's a. So just go from the left, see what value it approaches from the left. And then for the right, see what value it approaches from the right, and that'll be a positive. As you can see, they don't have to be equal. And here are some rules for limits. I'm not going to go over all of them. Many of them are pretty self-explanatory. For example, limit as x approaches a of 2 combined functions, you can separate it. Same with minus. For a constant, you can just remove it out. And yeah, so most of them are pretty self-explanatory. Just be sure to know maybe I guess all of these would be relatively important. You might see a few questions on them. Also know that you can manipulate equations to find a limit. So usually we just substitute. For normal functions with no issues, we can just substitute an x value in and find the limit by that. But for this example, x squared minus 36 over x minus 6, if we want to find the limit as x approaches 6, we can't just substitute 6 in because the denominator will be 0. So this is why we factor the top into x plus 6 and x minus 6. Then we cancel out the bottom x minus 6. Then we plug it in, and then we see it's 12. For the bottom one, we see there's this trig identity such that the sine of x over x is equal to 1. So 3 sine of 3x over 3x, 3x over 3x, we can just replace that with the value x, because they're the same. So it's just 3 sine of x over x, which is just 3 times by 1, which is just 3. Initially, we couldn't do as x approaches 0 because the denominator would be 0, as shown from the equation. Squeeze theorem. So squeeze theorem just relies on the idea if a function f of x always lies between 2 functions or in a certain interval, if the limits of h of x and g of x are equal to a value L, the limit of f of x must also equal that value L. This is kind of self-explanatory, but you might have to reference it on the exam. And you might need to manipulate the two functions h of x and g of x to get them equal to each other at a certain value. And then if f of x is guaranteed in between those two functions at all values, then you can find the limit of f of x that way. Okay, now I'm going to go over discontinuities. So an easy way to find a discontinuity is just, do you have to lift your hand if you're drawing the sketch? For example, look at all of these things I've drawn here. If you try to draw the graph, you'll have to lift your hand at some point. So that means all three of them are discontinuous. And here I have three types of discontinuities you need to know. There's a jump discontinuity, when it just jumps from one point to the next in a piecewise function. The point discontinuity, and also called as a removable discontinuity, where it's continuous, it's just not defined at that certain point. There's also infinite discontinuity, where there's a vertical asymptote. Also note that f will be continuous at c only if f of c exists, so it's defined at that point. And the limit of f of x as x approaches c has to be equal to f of c at that point. And for the limit to exist, the left-hand limit has to equal the right-hand limit. So those are all three constraints for a function to be continuous at a certain point. So here are some examples of commonly always continuous functions: polynomial, rational, power, exponential, log, and trigonometric. So in some ways, you can remove discontinuities. For a removal discontinuity, we can just redefine the function as a piecewise function. For example, this function, x squared minus 49 over x minus 7, is not continuous at x equals 7. But the limit is there. So this is how we can redefine it. F of x is equal to x squared minus 49 over x minus 7. Only at x equals 7 will the y value be equal to 14. And this essentially makes that function continuous at all points, and at x equals 7 in particular from before. So note that limits technically do not exist at infinite values, because infinity is not an actual number. It just means it'll keep increasing. However, we still add normal or left and right-hand limits for limits approaching infinity. So it can be positive or negative infinity. And the same limit rules apply. So if the left-hand limit equals the right-hand limit, then we can say that it'll be positive or negative infinity, or even if a normal limit equals infinity. Horizontal asymptotes. So we went over vertical asymptotes, that'll just be infinity. For horizontal asymptotes, essentially as x approaches infinity, so vertical asymptotes are when y approaches infinity or negative infinity. Horizontal asymptotes are when x approaches negative or positive infinity, then what y value is approached. So here on the bottom, I have this function, x to the power of 4 plus 3x cubed over x to the 6th. Now, how do we find out what y value is approached as x approaches infinity? One way to do this is just factor out x to the 6th from both the top and the bottom. So from the top, if you factor out x to the 6th, you get x to the 4 over x to the 6th plus 3x cubed over x to the 6th. On the bottom, if you factor out x to the 6th, you just get 1. And then x to the 6th cancels out on both sides. Then at the bottom, you just have 1. And on the top, x to the 4 over x to the 6th, as x approaches infinity, that'll just approach 0. For 3x cubed over x to the 6th, as x approaches infinity, that'll also just approach 0. So that's why the limit as x approaches infinity, or even negative infinity in this case, will be 0. The intermediate value theorem essentially just states, it's kind of logical, for a continuous function over a certain interval a, b, for any value c between a and b, there must be a value f of c in between f of a and f of b. So if c is the x value in between the x value a and the x value b, there must be a y value f of c, which is in between the y value f of a and between the y value f of b, if it's continuous over that interval. This just kind of makes sense, right? Because you're not going to get from one y value to another without passing every single value in between it, if it's continuous. Unit 2, basic differentiation. So how do we define average and instantaneous rates of change? So the average rate of change will not occur at just one instant. It'll be spread out. And the derivative just refers to the instantaneous rate of change at a point. You can estimate the derivative at a point by checking the slope of points nearby or by using a graph or a table. Also, that'll just be a tangent line. Think of the derivative as just a tangent line at a point. So you can represent the derivative with f prime of x, y prime, or dy dx, or d dx. And here are the two formulas that I went over at the start briefly, but didn't go into much depth in. We can use limits to define a derivative. So the derivative is just a slope, right? So f of x minus f of a over x minus a, except the limit will be as x approaches a. That'll make it instantaneous. And we can also do f of x plus h minus f of x over h. And the limit as h approaches 0, that'll also make it at f of x, and it'll make it instantaneous. So note that if a function is differentiable at a point, it must be continuous at that point. But if a function is continuous at a point, it does not have to be differentiable. The general rule of thumb is that a function must be smooth at a point. It cannot have abrupt changes to be differentiable. So here are two examples of non-differentiable points. So the first one is a cusp or a corner. It randomly turns at that top point, so you cannot differentiate at that point. And here's the vertical tangent. You can't really differentiate at a tangent because it'll be infinity. So yeah. And to find the derivative of functions, we use some rules. So here are some common rules. First is the power rule. The derivative of x to the power of n, you'll just bring the n down and have the exponent be n minus 1. Here's an example of that. 2x to the 7 turns into 14x to the 6. We bring the 7 down, multiply it by 2, 14, and then we do x to the 6. The constant rule, the derivative of a constant will just be equal to 0. Think of it as a slope, right? If y is equal to 5, that'll just be a flat line. There's no change at all. And the slope of that is just 0. The constant multiple rule. So is it the constant inside? We can take the constant out and just find the derivative of that function. And yeah. Here are some common derivatives you should memorize. So the derivative of sine of x is cos x minus sine x, e to the x, e to the x, ln of x, 1 over x, tan of x, sec squared x, cosecant x minus cosecant x cot x, secant x tan x, cotangent x minus cosecant squared x. And here are two more rules you should know. The product rule, the derivative of two functions multiplied by each other is f prime of x times by g of x plus f of x times g prime of x. The quotient rule, the derivative of both of them, of a quotient, will just be, think of it's just low d high minus high d low over low squared. So low times the derivative of the high one minus high times the derivative of the low one over the low one squared. And yeah, so when you differentiate, so if there's two different terms added or subtracted, just differentiate each term separately, and then each term separated by addition sign or subtraction sign separately. All right, next unit, more on differentiation. So we're going to first go over the chain rule. So in the chain rule, if there's a function inside a function, First, we take the derivative of the outer function and ignore the inner function, and then we multiply by the derivative of the inside function. For example, here, 3x plus 1 to the power of 5, we take the derivative of the outer function first, so that turns into 5 times by 3x plus 1 to the power of 4. And then we take the derivative of the inner function. The inner function is just 3x plus 1. So we multiply that by 3. So that's why it turns into 15 3x plus 1 to the power of 4. In implicit differentiation, essentially, we get dy dx in the equation. So usually so far, we've just covered differentiation with respect to y. So we differentiate x with respect to y. So in implicit differentiation, when we differentiate y, we use the exact same derivative rules, but at the end, we just multiply by dy dx. This is useful as we can solve for dy dx with implicit differentiation. So 7y to the 8, how do you differentiate that? First, we differentiate normally, so with the power rule, so 56y to the 7. And then at the end, since there's a y there, it's just the chain rule. So that's why we multiply by dy dx at the end. Note that if we were differentiating 7x to the 8, we wouldn't have the dy dx at the end. It's just that we're differentiating y. We have to multiply by dy dx at the end because we're differentiating with respect to y usually. And one more thing you should know in this unit is how to find the derivative from an inverse function. So let's say f of x is equal to y. That means for inverse function f minus 1, f minus 1 of y is equal to x. And because of that, we can relate the two derivatives to each other. So the inverse f minus 1 of y, the derivative of that is equal to 1 over the derivative of f to the x of f prime x. Note that the x and y are different. The x of one is the y of the other, and you plug in the corresponding ones to each other. And yeah, it's just 1 over the derivative. Just memorize this formula. And here are inverse trigonometric derivatives that you should know. First one, sine minus 1 of x is equal to 1 over square root of 1 minus x squared. Cosine minus 1 of x is equal to minus 1 square root of 1 minus x squared. And tan minus 1 of x is equal to 1 over x squared plus 1. Cotangent minus 1 of x is equal to minus 1 over x squared plus 1. Secant, inverse secant x or arcsecant x, 1 over absolute value of x times by x squared, square root of x squared minus 1. And the cosecant one is just minus 1 of that. So note that you only have to memorize 3. Memorize the sine, the tangent, and the secant. And the other 3, cosine, cotangent, and cosecant, are just the minus ones of the corresponding ones. Okay, so note that you can differentiate to higher orders. So let's say we have a function y. First derivative is just y prime. We can differentiate that again, and then we'll get the second derivative, y double prime. And you can keep doing that. And if you can, a function has to be like x differentiable, or in this case, twice differentiable, to be able to get the second derivative. Okay, unit 4, contextual applications of differentiation. So how do we interpret a derivative in context? The derivative of h of x is the rate of change of h. The derivative of h of x is the rate at which the rate of h is changing. So derivatives are just the rate of change. The second derivative will be the rate at which the first derivative is changing. And here's an example. If h of t is position, derivative of h of t with respect to time is velocity, and the second derivative will be acceleration. So here let's look at units. So first, h of t position is just meters, then velocity meters per second, and the acceleration meters per second squared. Also note that this is just one context of derivatives. It can be used in many contexts, not only motion. For example, how much money someone earns. You can find the rate at which the money someone earns is changing. And here's just what I said on the last slide, but in equation format. X of t, x prime of t is equal to v of t, x double prime of t is equal to v prime of t is equal to a of t. the absolute value of v of t is equal to speed. And we use the sign of x, v, and acceleration to describe motion. So if you've been in physics, if x is increasing, so position is increasing, that means v is positive. But if, let's say, velocity is increasing, but let's say velocity is positive and acceleration is negative, that means it's slowing down. If velocity is positive and acceleration is positive, that means it's speeding up. And yeah, we can just use the signs of these to describe motion. Okay, now I'm going to go over related rates problems. So how do you solve related rates problems? First, you write an equation, relate what they're saying in the problem to an equation, then we differentiate using chain rule. For example, let's say we're looking at a problem for the volume of a sphere. First, we'll say v is equal to 4/3 pi r cubed. And then we'll differentiate. So dv dt, the rate of change of the volume, is equal to 4/3 pi times by 3r squared, derivative of r cubed, times by dr dt from the chain rule. And then with this, we can solve for certain values. We can solve for, based on the volume and the radius, we can solve for the rate at which the radius is changing. Based on the rate of change of the volume and the rate of change of the radius, we can solve for the radius at that point. And based on the rate of change of the radius and the radius at a point, we can solve for how fast the volume is changing. And yeah, this is just one basic example of related rates. Okay, now I'm going to go on to linearization. So first, we should go over what a tangent line is. A tangent line, you just draw a tangent line to a point, and it's just the linear approximation of the function near the tangency point. And we can write it using point slope form. Here's one way to write it. Y minus y1 is equal to m times by x minus x1 for any given coordinate x1 and y1. Another way is just y is equal to mx plus b, and we can rearrange this equation to have that, y equals mx plus b. So first we find the slope by finding the value of the derivative of the function at that point we chose. So x1, y1. We choose a point that we want to find the equation at. We find the derivative at that point, and yeah. Then we use the same coordinate that we chose. We plug it into the equation above, and we get an equation for the line. And then we can use that equation to estimate values based on that line. And yeah, note that the tangent line will be drawn from the point that we choose. And that tangent line we choose will be used for estimation. So logically thinking, a concave down curve will result in an overestimate, and a concave up curve will result in an underestimate. I'll show you guys on the next slide what I mean. So here, the first curve on the left, it's concave up. And as you can see, if we linearize it, if we use linearization to approximate values, it will clearly be an underestimate because all the values are below. But from the second one on the right, if it's concave down, it'll be an overestimate since all the line values are above. Last topic is L'Hopital's rule. So if substitution, when determining limits, is just using substitution, if it results in an indeterminate form, that means 0 over 0 or infinity over infinity, only then we can use L'Hopital's rule. So then we will replace the numerator. We'll find the derivative of the numerator, replace the numerator with that, find the derivative of the denominator, replace the denominator with that, and we make sure we do it separately. We're not using quotient rule. We're just finding between the numerator and denominator separately, finding the derivative separately, and just putting it back in. And then we'll try substitution again. And if it does not work, we'll use L'Hopital's rule again. And we keep going until we find a value that's not indeterminate. Unit 5, Analytical Applications of Differentiation. So first we're going to go over the mean value theorem, and that's just MVT in short. So all it says is that if a function is continuous on the interval a, b, so closed interval, a and b is included, and differentiable on the open interval, a, b, so that means a and b are not included, there has to be some point c such that the derivative at that point c equals the function's average rate of change throughout the entire interval. And yeah, this is a really powerful theorem. You just have to make sure that the two conditions are met beforehand. Okay, now I'm going to go over the extreme value theorem and what are critical points. So if a function is continuous over a certain interval, there will have to be one minimum and one maximum of y on that interval. This is sort of self-explanatory. Over a certain interval, there has to be one minimum and one maximum at least. Local or relative extrema refer to max and min values within a certain interval, and global/absolute extrema refer to min and max values within the whole function. Critical points are where the derivative of a function is equal to 0, and we check the derivative sign of values just on the left or the right of critical points to determine if a function is decreasing or increasing in that region. Also note that a function will not change. It will not change from increasing to decreasing unless it passes the critical value. So the first derivative test. The first derivative test is essentially at spots where the first derivative equals 0. We check the left and right sides. If the left side, the function is decreasing, so the derivative is negative, and on the right side, it's positive, meaning it's increasing, it's a local minimum. If the opposite true, it's a local maximum. These two diagrams show what I mean. So initially, the function is decreasing on the left side, then it reaches the critical point where its derivative is 0, and then starts to increase. That's a minimum. On the other hand, a function is increasing on the left side. It reaches where the derivative is 0, and then it decreases. That's a local maximum. The candidates test essentially is used to find extrema. Candidates are all the critical points in an interval, so all the relative minima and maxima, they're possible candidates, and both of the endpoints of an interval. So then in the candidates test, we take all of our potential candidates, we plug in our x value into the original function. And then with that, then we compare all the y values. Based on the y values, we find the largest, smallest ones, and then we can use that and we find all of the extrema. To find global extrema, we just let the interval be the entire domain of the function. The second derivative test. So first, let's note that inflection points are points where the second derivative of a function equals 0. And the second derivative just means that the rate of change of the first derivative is 0, when it's 0. And then we can check values next to these inflection points to find areas where the first derivative is increasing or decreasing. A positive second derivative means the function is concave up. A negative second derivative means the function is concave down. Concave down looks like an upside down U, and concave up looks like a U. For the second derivative test, we just plug in critical points. So values where the first derivative is 0, we plug that in to the second derivative, and then we check if it's positive or negative. Positive means the local minimum, negative means the local maximum. So this is the same thing as the first derivative test we went back. Essentially here, instead of checking both sides, we can just see if it's the second derivative is positive or negative. So positive means a local minima, because positive second derivative means the first derivative is changing from negative to positive, as seen here. For local maximum, the second derivative will be negative, because as you can see, it's changing from positive to negative. Furthermore, we use critical points and inflection points to connect a function to its first and second derivatives. Okay, now I'm going to go over optimization. So in optimization problems, we essentially are given a real-world application, and then we try to find the maximum and minimum values. We try to optimize a function. So first, just picture the problem with the diagram, and then use your problem-solving skills and create an equation for what you are finding. And make sure, have it all be represented in only one variable. Then we find the critical point, and we use the candidates test to find the values, which will result in what you're looking for. So if we're looking for a max value, we'll find the candidate that results in the max value. Min value, we'll find the candidate that results in a min value. Implicitly defined functions. So in implicitly defined functions, yeah, so I'll go more in depth on the next slide, but for implicitly defined functions, it'll have x and y in it. And yeah, on both sides. So we will look for points where the derivative is 0 or undefined. We solve for y in terms of x, or we solve for x in terms of y. And then we recreate the original equation in just one variable and solve for the critical points. So here we have this implicitly defined function, xy cubed plus x6 plus equals 3y. We implicitly differentiate on both sides. Then essentially we just solve for y prime. And from the bottom we have y prime. Then now all we do is look for critical points. And critical points here will be where the function is 0 or is undefined. So that means that the numerator is equal to 0 or the denominator is equal to 0. And as you can see here, since we have both x and y's, we'll essentially solve for x or y. We'll solve for one of them. Let's say we're working with the numerator first, so then we'll have y cubed is equal to negative 6x to the 5. We'll solve for y, and we'll plug it back into the original equation and find, then it'll just be one variable x, and then we'll find the corresponding x value that works and the corresponding y value. Then we do the same thing with y, see if it has a different value, find the new corresponding x and y values, and then we repeat the same process with the denominator. Unit 6, integration and accumulation of change. This unit is pretty hard. It'll introduce integration, as so far we've only done derivatives. So what is accumulation of change? So the area under the curve is defined as the total area between the x-axis and the function. So it can be negative or positive. The area under the curve of a rate of change function gives us the accumulation of change. Think of the area in physics, think of the area under the curve of velocity time graph. That'll give the net displacement. So the rate of change function is velocity, and the area under the velocity time graph gives us the accumulation of change, which is just the net displacement. The units for area under the curve is the y unit times the x unit. So in here, it'll be seconds times meters per second, which is just meters. The y-axis unit is meters per second, the x-axis unit is seconds. Okay, now I'm going to go into Riemann sums. So Riemann sum is the way of approximating the area under the curve. So essentially, you split up the Riemann sums into n subintervals, and the width of each rectangle is the x interval, the total x interval length, divided by n. That'll be the individual widths, n times. A higher n means a better approximation because it'll mean a smaller interval length, so more approximations. For a left Riemann sum, the left value of each interval, the left x value, that'll be used as the top horizontal line. For a right Riemann sum, the right value, the right corresponding y value for the x value will be used as the top horizontal line. For a midpoint Riemann sum, essentially, we'll look at the middle value. So the two x values averaged out to the middle one, we'll look at the y value, and that'll be the height. For a trapezoidal Riemann sum, we'll connect the two y values, the two y values for each of the corresponding x values at the endpoints. We'll connect them using a straight line, and then we'll use a trapezoid area formula to sum it up. And so in general, a left Riemann sum will always be an overestimate over a decreasing interval and an underestimate over an increasing interval. This makes sense, right? Just draw an increasing and decreasing function and you'll see how it's an over/underestimate. The right Riemann sum is the opposite. A trapezoidal Riemann sum will be an overestimate in a concave up graph and an underestimate in a concave down graph. A midpoint Riemann sum will be an overestimate in a concave down graph and sorry, I put overestimate for both, but it should be a midpoint Riemann sum is just going to be the opposite of the trapezoidal Riemann sum. So overestimate in a concave down graph and an underestimate in a concave up graph. Here's an example of a right and left Riemann sum. On the left side, I drew the right Riemann sum. As you can see, we're taking the y value of the right x corresponding y value at each subinterval. And here, as you can see, it's an underestimate. And on the right, we have a left Riemann sum. We'll take the corresponding left value for each of the rectangles. And then, yeah, we'll take the corresponding left value. I also drew a midpoint and a trapezoidal Riemann sum. The midpoint, we're always taking the midpoint of the interval, as you can see here. And for a trapezoidal, we're going to be drawing a trapezoid, a line in between the 2 points. So it's not going to be a straight line, it's going to be a triangle, which will make it a trapezoid. Okay, so you all need to know Riemann sum notation. So for a Riemann sum, as n approaches infinity, we get the true area under the curve, as the Riemann sum approximates better with the larger n value. So for an interval a to b, the limit as n approaches infinity of the sum from k equals 1 to k equals n of b minus a over n times by f of a plus b minus a times by k over n. This is the actual area under the curve. And that limit equation is equal to the integral that represented on the right, the integral from a to b of that curve. N is the number of subintervals, and k will be the kth subinterval. Essentially, these two are equal, and then you'll be able to convert between both of these at any given point. Okay, now I'm going to go into the fundamental theorem of calculus, the FTC. Essentially, it's just that derivatives of integrals are inverses of each other. They cancel each other out. If you take the derivative of an integral of a function, you'll just get that function. As you can see from what I wrote here. Yeah, so let me see. The derivative, also you need to know that the derivative of a function from a, if the lower bound is a and the upper bound is a function g of x, then we have to use chain rule. So that'll just be equal to f of g of x times by g prime of x. Yeah. And the bottom one, if it's two functions, then we just have to use chain rule again, but we have to subtract because it starts at the bottom function and ends at the top function. That'll be f of g of x times by g prime of x minus f of h of x times by h prime of x. Yeah. All right, continuing on the fundamental theorem of calculus. The integral from a to b of a function f of x is just the antiderivative f of b minus the antiderivative at a. So yeah, just the difference in values for the antiderivative of that function. That'll be the same as the integral. Okay, and integrals have some properties. Here are the properties you need to know. The integral between, if the x is the same, a to a, the integral will be 0. That just makes sense, right? Because it's not over any x distance. And also the integral from a to b of f of x, you can think of it as just the negative of the integral from b to a of f of x. So if you switch the a to b to a, it'll be negative. Furthermore, if there's a constant, you can take it outside the integral. And also you can split up an integral. So from a to c, you can make it a to b, and then from b to c. And finally, there's addition and subtraction. You can split up an integral of two functions added to each other. You can take the integral separately and add them or subtract them to each other instead of doing it at once. All right, so the antiderivative of a function is a function f of x whose derivative is lowercase f of x. So when we take an integral, we actually take the antiderivative of a function. And actually, it was not intentionally seen by Newton, it just happened to be discovered that the antiderivative is the same thing as the integral. So to find an antiderivative, we just reverse the steps of the normal derivative rule. So if you know all the derivative rules well, we'll be able to easily find antiderivatives. For example, here, x of 5, right? The antiderivative of that is x to the 6 divided by 6. For example, when we use power rule, 6 will go down and it'll just be x to the 5. And we always add a constant c, because remember, when you take the derivative of a constant like 5, it just turns to 0. So that's why we can't really know what it is. Well, later we'll find out how to solve for it. But yeah, for right now, we just add c to the end of any time we antiderive. All right, so finding antiderivatives. So initially, we'll always add a constant c to all antiderivatives. And we can find a particular solution. We just need the y value for a certain x value, and we'll plug it in. We'll solve for c by plugging in the corresponding x and y values. And yeah, we can solve for c that way. Also note that the antiderivative of 1 over x is ln of x. So don't try to use any power rule on that. All right, now I'm going to go into use substitution. So essentially, if we have to use chain rule to take the derivative, then we'll require use substitution to take the antiderivative. And when we choose the u, we need to think about the derivative, and we want the x's to cancel out. Here's an example I solved. Let's say we want to take the integral of x plus 1 squared dx. Then let's say u to be x plus 1. So then it's the integral of u squared du, and that just turns into u cubed over 3 plus c. So when we say u to be x plus 1, we take the derivative of u with respect to x. So du dx is just equal to 1. And that's how we get du is equal to dx. In other cases, du might be equal to 3 dx or 4 dx or x dx, for example. And then we'll just plug in we'll replace the dx with what value we got. And then also note that, so then if it's a definite integral and we want to find a value over a certain range, like 0 to 2, for example, then if we do u sub and we get it all in u's, we can do two things. We can replace all the u's back to x's and use the interval we got, 0 to 2, or we can keep it in u's and then just convert all the x's to u's. For example, x is from 0 to 2 here. We'll plug in x is equal to 0, so the starting range for u is 3, and the ending range for u is 7. Then we'll keep the u's. We will not convert to x. We'll keep the u's, and we'll find the integral of that u function from 3 to 7. Or we can just convert them all back to x's. It doesn't matter. It'll give the same answer in the end. Okay, and doing long division and completing the square can help when taking the integral. So let's say we have a function, like a rational polynomial on the top divided by x minus 5 or x minus 10, for example. Instead of taking the integral of that whole thing, we can just do long division. And then take the integral of the quotient that we get. So the final remainder will be something like 15 over x minus 10, for example. And then, so we'll integrate normally. And then at the end, 15 over x minus 10, for example, that's just going to be 15 ln of x minus 10. And yeah. We can also complete the square to help us take the integral. So let's say, completing the square is just x squared plus bx plus b over 2 squared. That'll be the form. And then when we complete the square, it'll just be x plus b over 2 squared. And then, so when we complete the square, we'll still have to make sure nothing is, like, we don't add anything because we can't change the function. So if we add a value to get the final term b over 2 squared, we have to subtract it outside the square to make sure the net value added is 0. So then we'll do x plus b over 2 squared. That'll be the squared value. And then we can either integrate from there, or we can do u sub. We can set u to be equal to x plus b over 2. and use substitution. Either way, that'll make finding the integral much easier. All right, now I'm going to go over integration by parts, and this is a BC only topic. So essentially, what I drew here summarizes integration by parts. So the integral of f of x times by g prime of x will just be equal to f of x times g of x minus the integral of f prime of x times by g of x. So if there's two functions, we should choose f and g prime carefully. Determine which one's easier to differentiate and which one's easier to integrate, and yeah, choose them accordingly. So let's say a function is easier to differentiate, then we'll probably want to have that be f of x. But if a function is easier to integrate, we'll want that to be g of x. And yeah, so a quicker way to do integration by parts is through tabular integration. So let's say we have this function x cubed sine of x, and we want to find the integral of it. We'll use integration by parts. So for our f of x here, we're going to choose that to be x cubed because it's easy to differentiate, and it's going to eventually go down to 0. So choose the one that simplifies first, choose that one to be your f of x, and yeah, so keep finding the derivative of it until it gets to 0. Then have the other function be g of x, keep finding the integral of it until it becomes 0. And then what you do is you draw lines. So from the first f of x value, you draw to the second g of x value, and then so on. You keep drawing those diagonal lines, and then you alternate. So first it's plus, then minus, then plus, then minus. And yeah, so, and then you can write out what it'll be, and that'll give you the final integral much easier. So that'll end up being, in this case, it'll be minus x cubed cosine x plus 3x squared sine x plus 6x cosine x minus 6 sine x. And yeah, so tabular integration is essentially if you do integration by parts once and you still get an integral on the other side, you're not able to simplify it, then you need to do it again, right? But tabular integration speeds up the process so you get a final answer right away. All right, now I'm going to go into linear partial fractions. So for a function f of x is equal to p of x over q of x, if f of x is a proper rational function, so the degree of p is smaller than the degree of f, then we can use partial fraction decomp. Essentially, how it works is that q of x can be broken down into linear factors. And then we rewrite p of x over q of x as a1 over f1 plus a2 over f2 plus an over fn, or dot 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 an over fn, and so on. And this is assuming q of x has n non-repeating linear factors. So here's an example. Let's say I want to take the integral of 1 over x plus 3 times by x minus 3. So the first step is that I'll rewrite it as a over x plus 3 plus b over x minus 3. Then I'll multiply by x plus 3 times x minus 3 on both sides. So then that just turns into 1 times 1 is equal to a times x minus 3 plus b times by x plus 3. Then we just find a and b. So to find a, we set x is equal to minus 3. Then the b cancels out, and we get a is equal to negative 1 over 6. For b, we set x is equal to 3, and we get b is equal to 1 over 6. And yeah, so this is what we get for the integral. Integral of minus 1 over 6 over x plus 3 plus 1 over 6 over x minus 3. And this is much easier to integrate. All right, now I'm going to go over the final one, improper integrals, which is also a BC only topic. So these are integrals which have infinite limits of integration, or will have an infinite discontinuity. It's pretty self-explanatory. Essentially, we just use limits. So f of x must be continuous on the interval specified. And yeah, so first one, the integral from, if you want to take the integral from a to a value a to infinity of f of x, then we did the limit as t approaches infinity of a of the integral from a to t of f of x. And yeah, so then we'll just find the integral of f of x and then use limits and find the limit. And yeah, we can do the same thing for negative limits. So let's say we want to take the integral from negative infinity to b of f of x. Then we'll do the limit of t as t approaches negative infinity of t to b of f of x d of x. So we'll find the integral and take the limit, and we'll find the value it approaches to. So if the limit does exist, the integral will converge to that number. Otherwise, it'll diverge. Diverge, it could go to infinity or negative infinity, for example. And yeah. So continuing on improper integrals, if you want to take the integral from negative infinity to infinity, we can do the same. We can do something similar. So we can do the limit positive as t approaches negative infinity from the integral from negative infinity to 0 of f of x, and then we just add that to 0 to t, the integral from 0 to t as t approaches infinity. And yeah, this is pretty self-explanatory. It's pretty similar. You'll use the same steps as before. Find the antiderivative and take the integral. And last one, if there's an infinite discontinuity at b, then the integral of f of x from a to b is the limit as t approaches b from the left side of a to t of f of x d of x. On the other hand, if there's an infinite discontinuity at a, we'll do the limit as t approaches a from the right-hand side. Yeah, from the right-hand side, and the integral from t to b, f of x dx. Okay, unit 7, differential equations. So we can use differential equations to model situations. We may have to calculate a k-value, and we also may need to write an equation for the second derivative. It's pretty self-explanatory. Here, dA dt, it can be directly proportional, k times by f of t, inversely proportional, and f of t can be like a value can be a squared value, a cubed root, a square root, and so on. It just depends what the problem gives you. For example, if it says that the rate of change is proportional to the square of a function, it would be f of t squared. Okay, slope fields. Slope fields essentially just represent a differential equation. It just shows the slope at every single given coordinate. Here I drew a slope field for dy dx is equal to 5x. At x equals 0, for every x equals 0, the slope is 0, as you can see here. For every x is equal to 1, the slope is equal to 5, as I drew there. 2, 10, minus 1, minus 5, minus 2, minus 10. And so you should be able to identify slope fields and be able to sketch them. All right, now I'm going to go into Euler's method. This is the BC topic. All it does is helps to find an approximate solution to a differential equation. And when you're using this method, be sure not to round early, as that'll give an error at the end. So I drew this small diagram on the left side to kind of represent what I mean. As you can see, I have one curve. That's the actual function. Euler's method will be using slopes at different points to approximate the value at that curve at a certain x value. So essentially, we'll first find the change in x, which is the x step value. So to do that, we'll find the change in x over the total range. Let's say we want to find the x value at x equals 5, but we have the x value at x equals 1. It'll be 4. And let's say we want to do it in 3 steps. We'll divide that by 3. And that's how we find the step value. And number 2, then essentially, we'll go one by one and find the derivative at every single value that we encounter. So the final y will be equal to the initial y at that point, plus y prime, the derivative times the change in x at that x value. We'll do that every time until we get to the final y value. And yeah, as you can see, from the curve I drew, initially we draw one line, then we draw the next line, then we draw the third line, and then we get to the end. That's all step 2 is doing. And then we repeat step 2 until we get the y value to be equal to the final y value. And then that's how we'll approximate it. I mean, technically, it'll honestly be the final x value, because we're gonna, the question will probably be like this. If a function at x of 0 is equal to 1, based on, let's say its derivative is equal to something, I don't know, and then approximate using Euler's method the value of the function at x equals 5. Then we'll essentially we're just repeating until x is equal to 5, and then we'll get our final y value, and that'll be our approximation. Okay, now I'm going to go over separation of variables. So this is a pretty important topic. It helps us find an actual function from a differential equation. So in separation of variables, all we do is separate the variables and integrate, and then we'll get an equation for y. And we're going to have a c at the end, the constant. If we have the x and y values given, we can solve for c, and then we can get an actual definite function. At the end, be sure to verify that if we have the point, the function actually goes through the point for the equation that we get. Also, note, if we get rid of an absolute value, we have to consider both cases. Let's say here I have an example, absolute value of y is equal to minus x squared plus 6. Then the two cases are y is equal to x squared minus 6 or minus x squared plus 6. We need to consider both of the cases and see which one works. On the right side, I have a step-by-step solve through process. So dy dx, let's say it's equal to x cubed over 2y. First, we'll separate the variables. We'll send 2y on the other side to the dy side, and send dx to the x cubed side. Then we take the integral of both sides, and then we get y squared plus 1 over 4 x to the 4 plus c is equal to 1 over 4 x to the 4 plus c. Then we can just square root both sides, and we'll get plus or minus and that. That's really all it is. And yeah, sometimes you might have to plug in a value to solve for c. Okay, exponential models. So all you know about exponential models is that they increase at a rate proportional to the y value. And they can be modeled by this equation. Y is equal to a b to the t. A is the initial value, b is the growth factor, and t is the time. So if we take the derivative of this, it actually just turns to y ln of b. And this is because if we take the derivative using the chain rule, it'll just be ab to the t times by the derivative of b to the t. And then ab to the t is just y. And then ln of b is just a constant. Because the growth factor is a constant, it will not be changing. That's why we can just say k is equal to ln of b, and we can rewrite the derivative of an exponential model as ky, a constant times by the y. So it's directly proportional to the y value. We can also, then if we rearrange it, if we use separation of variables to solve for y from the derivative formula, we'll get y is equal to c, which is the initial value, times by e to the power of k times by t. K is a constant, t is the time, and c is the initial value. This final equation is essentially what you need to know. And yeah, be sure to know it, as a question on the exam will ask about this specifically. All right, now I'm going to go into logistic models. I believe this is the last topic in this unit, and it's a BC only topic. So here is a graph of a logistic model. Essentially, it's going to be increasing. It's going to be concave up at a point, and it's going to switch and be concave down and approach a certain value, L. The max value it approaches is L. In the context of a population, that L can be thought of as carrying capacity. And note that the max growth rate, the max derivative, the max slope value will be at y is equal to L over 2. That's where the max rate will occur. And essentially, we can represent this derivative of a logistic model in two ways. One, dy dt is equal to ky times by 1 minus y over L. K is a constant, L is the limiting value, or it can be represented as K over L, y times by L minus y. So if you recognize this in the question, know it'll be a logistic model. And yeah, just be sure to recognize it and solve for these values. And know that the max value is L. They might ask you about that to find the max value and find out where the max growth rate occurs. And the max growth rate also occurs at the inflection point where it changes concavity. Unit 8, applications of integrals. Okay, first we're going to go over the average value. So the average value, think of it as just, well, it's just an average. The average value a function will take on a certain interval. And you can find it by this equation, 1 over b minus a, and that means it'll be from the interval a to b, multiplied by the integral from a to b of f of x. This kind of logically makes sense. It's the total accumulation from that space divided by the total length of that space. Okay, and we can also relate integrals to physics. So position as a function of time is just the integral of velocity. Velocity as a function of time is the derivative of position, as we went over before, or the integral of acceleration as a function of time. And acceleration as a function of time is the derivative of velocity or the second derivative of position. And you should be able to apply derivatives and integrals to different type applications. Of course, physics is just one of them, but also you can apply to applications like the rate at which water enters the tank, and so on. Okay, now I'm going to go over how to find the area between curves. So far, when you've taken the integral, that's essentially been the area between the function and the x-axis. So how do you relate it to different axes? So essentially, the area between two functions is from a to b is f of x minus g of x, the integral of that. It's pretty straightforward. Just make sure f of x is greater than g of x, because it's the first one and the g of x is being subtracted. Again, a normal integral that we've done so far before this moment, it would just be f of x minus 0, minus x equals 0. But yeah, we can apply to different functions as well. And by the way, this is for representing function as y as with x's. So y equals x squared, y equals square root of x, or so on. And we can also set up an integral based on its y values. So that means for these two curves I have shown, we would solve for x, and that would make x is equal to y over 5 here, for example. Or on the second curve, that would be x is equal to the square root of y. And note that it could be positive or negative square root of y, but here, since it's on the right side, it's positive square root of y. So essentially, we just solve the function in terms of its y value. We solve for x. We get x is equal to some form of y. And yeah, and then essentially here, since we have it expressed in terms of y, it's going to be the right curve minus the left curve. It's not the top or bottom curve anymore. It's going to be the right minus the left. And that's how you'll find the area between them. So in this case, it'll be the integral of the square root of y minus y over 5 dy. In different scenarios with different functions, use either express it in terms of y or x, depending if it's top and bottom or left and right. Continuing on areas between curves, you may need to do more than one integral if the curves intersect at more than 2 points. Always make sure that the bottom or left function is being subtracted from the top or the right function. And yeah, you may just need to do more than one integral if they intersect at many points. For example, if one point f is higher than g, but at another point g is higher than f, you'll just have to do multiple integrals to get the sign right. Or you can just do the absolute value, and then you can use your calculator. Absolute value will always just give the one on top minus the bottom. It'll give that net value. Okay, now going on to volumes with cross sections, specifically squares and rectangles. So essentially, a problem, you can imagine this curve I've shown here as the difference in height between both the curves. That's just the side length. Think of that in the problem, it could just say that that is the side length of a square. And then you need to find the volume of the thing that results from the difference between the two functions. So for a square, this is how you do it. It's the integral of f of x minus g of x squared. This makes sense, right? Because it's a square, the sides, the area is just s squared, and then you integrate it. So it'll be a ton of squares added up. The area of a ton of squares added up, but that's how it becomes 3 dimensions and turns into a volume. It can also be a rectangle. For rectangle, it'll just be f of x minus g of x, the top minus the bottom still. And it's not going to be squared here because they'll usually give the height in the problem. It could be 3x, for example, or it could just be 3, and it depends. And yeah, you'd find the integral like that. So check for the shape if it's a square or rectangle, and you can still convert it. You can still convert this into the y. So that means you can express it in terms of y. So then if you express it in terms of y, it would just be right minus left. And then you would use the y-axis. So for a definite integral, it would be from y equals 0 to y equals 5, for example, not the x values. And yeah, you could just convert it to y2, depending on the problem. So it'll say, if it says perpendicular to the x-axis, do it normally like this I have on the screen. If it says perpendicular to the y-axis, you'll have to change it and express it in terms of y. All right, now continuing, the last two, we did squares and rectangles. Now we're going to do triangles and semicircles. For an equilateral triangle, so it's going to be the same. Essentially, the difference in height is going to form a cross-sectional area of a triangle, equilateral triangle, isosceles right triangle, or a semicircle. So if it's an equilateral right triangle, you'll use this equation, square root 3/4 times f of x minus g of x squared, the integral of that, over any certain range. If it's an isosceles right triangle, it'll be 1/2 f of x minus g of x squared. If it's a semicircle, it'll be 1/2 pi times by f of x minus g of x over 2 squared. And yeah, again, the same rules apply. So you might have to convert it into expressing it in terms of y for these as well. All right, now going on to the disk method. So in the disk method, you essentially just take the area of something and you revolve it around an axis. You revolve it in a circle, and then that's how you get a solid of revolution. So here on the right side, I drew a diagram of a sort. I drew this function, and then when you revolve it around the x-axis, it's just going to spin. And when it spins, you see it's going to form those circles at those various heights. And then it'll do that for every single point in between two. And yeah, that's one way to imagine it. I know it's kind of complex, but just bear with me. And then to find the volume of that, it would just be the integral of pi times the radius squared. And here the radius is just going to be the distance between the axis, which in this case is going to be the x or y axis, the axis of revolution, and the outside of the solid. So here the distance would just be f of x. Note that even though here it looks like 2f of x, the radius is still f of x because the radius is just half the diameter. And yeah, that's how you find the volume of a solid of revolution. Okay, so how do you do this with other axes? So essentially, you'll just do the function minus the axis, and then the same equation. It'll be r of x minus the new axis squared. And it can be done for x or y values. So in this case, I have this function, and then I'm revolving around the y equals 2 line, which I drew here. And because it's revolving around the y equals 2 line, I'm gonna have to subtract 2. And that's how you'll make sure you're always getting the correct height, the correct distance between the axis that you're rotating around and the function. And then it'll be that squared times by pi outside the integral. And yeah, also note that even if it's a negative axis, it might get kind of confusing. Just still do curve equation minus the axis of rotation. So think about it here. If it was y equals -2, it would essentially be the curve equation minus -2. So it'll just be +2. And that makes sense, right? Because since it's revolving around the negative axis, the height gets 2 extra units. And yeah. Okay, now going on to the washer method. So we went over the disk method, but what do you do if there's a gap? If you want to create a solid revolution, but there's a missing area. So here I have an example. I have this cross-sectional area. And then let's say I want to revolve it around the x-axis. You see I drew the dotted lines. There's a gap there because it's the cross-sectional area of two functions. So if you revolve it around the x-axis, there's going to be a hole in between. And as you can see, I drew a washer kind of on the right side. It essentially, the outer white part, the inner white part is going to be that blank spot that's not included, and the outer white part is what we actually want. So we can't just do the outside function, right? So essentially all we do is the outside function squared minus the inside function squared and the integral of that times by pi. And note this is different because we're not doing r of x minus small r of x squared. We're doing r of x squared separately minus lowercase r of x squared separately. Think of it, it's literally just two separate integrals. I just combined it to make it easier. So be sure not to mess that up. Okay, and how do you do the washer method around different axes? So let's say here I'm doing it around the y equals 3 line. Essentially, you just look at the diagram, make sure you find the right distance. And in this case, if you find the right distance, it's going to be, since the bottom curve is f of x here. So find out which one is going to be the outer curve and which is going to be the inner curve. In this case, the outer curve is f of x. And you want to find the distance between the y equals 3 line and f of x. So that's the first dotted line that I drew. So that's 3 minus f of x squared. Then you want to find the distance between the dotted line, y equals 3, the axis of rotation, and the second curve, the inside curve. And that'll be g of x. So that's why you subtract 3 minus g of x squared. And then you find the integral of that. And that's about it. Again, the same thing applies if you want to do it in respect to the y-axis. If you want to rotate it around or if you want to rotate around an x equals 2 line or an x equals line, or even if it's a negative number. If it's a negative number, just draw it out. Make sure, just understand it. Make sure you're getting the right distance from each of the curves and create the integral that way. Okay, and last topic, this is a BC only topic. Essentially, how do you find the arc length of a curve? And the proof is pretty complex, but you don't need to know that for the scope of the course. All you need to do is you make sure the curve is smooth and continuous. And essentially, it just approximates a ton of tiny, tiny intervals. And yeah, that's how you get it. So the formula is just the integral from a to b of a function of the square root of 1 plus f prime of x squared dx. And you're going to find, and that's going to give you the arc length from a to b of f of x. And yeah. Okay, unit 9. So for the Calc AB kids, I guess that's the end of the course. And yeah, so to study for the exam, just make sure to practice test, understand the concepts, and do time test. Okay, now unit 9. Unit 9 and 10 will just be purely BC units. Unit 9 is parametric equations, polar coordinates, and vector valued functions. So a parametric equation, essentially, it doesn't have x and y. It'll represent x as a function of a new parameter like t, and it'll represent y as a function of that same parameter t. So the derivative of a parametric equation, dy dx, is equal to dy dt over dx dt. It's pretty self-explanatory. Think of it as just y prime over x prime. And essentially dx dt cannot be equal to 0, otherwise it'll be undefined. Okay, how do you find the second derivative of a parametric equation? So essentially you just find the derivative of the first derivative, and you do it with respect to t, and divide that by the derivative dx dt. And yeah, so you'll get, when you find the first derivative, you'll have dx dt already stored. You can just use that same dx dt. And yeah. That's it. Okay, so remember in Unit 8, we went over arc lengths. So how do you find arc lengths for parametric curves? Essentially, it's just this equation, the integral from a to b of a parametric curve, and the integral of the square root of dx dt squared plus dy dt squared, dt. Yeah, that's it. Okay, so now we're going to go over vector valued functions and how do you differentiate them. The vector valued function, it'll have two components. Here I drew one, r of t, and the first component, the function will be f of t, and the second component, the function will be g of t. And this can model velocity, it can model position or anything. So generally the first component will be the x value of position, if it's modeling position, for example. The second component will be the y value of position. So how do you differentiate these? You essentially just differentiate each function separately. So r prime of t will be f prime of t in the first one and g prime of t in the second one. And the same derivative properties still apply. If you have to use the chain rule, then you'll first take the derivative of each of them, then you'll plug in the new value for t that you got in, and then you'll multiply both functions by the derivative of the value plugged in for t. And the last part is the chain rule part. So let's say we want to do the derivative when r is equal, do you want to do the derivative of r of 3t cubed? So first we'll take the derivative of the inside functions, then we'll plug in 3t cubed for t in each of them, and then we'll take the derivative of 3t cubed, which is just 9t squared, and multiply both of the inside functions by that. And yeah, so again, note that the first function is the x function, the second function is the y. Okay, so integrating vector valued functions. This is a pretty straightforward thing. If you want to find the integral of a vector valued function, you'll find the integral of both of them separately. So the integral from a to b of f of t and the integral from a to b of g of t. And here I have some values for r of t, which can be thought of position, v of t velocity, a of t acceleration. So again, you already know this from before, but to find the derivative, you can relate each of them. So v of t will be x prime of t, y prime of t. A of t will be x double prime of t, y double prime of t, or v prime of t, and or the v prime of t. And for speed, since speed just cares about magnitude, it'll just be x prime of t squared plus y prime of t squared square rooted. And be sure to know how all these relate to each other. So on questions, you can relate back and forth between each of these and also using integrals. Okay, now I'm going to move on to polar form. So polar form represents functions in r and theta. So usually we've done Cartesian coordinates, x and y. So polar form will represent in r and theta. So in general, x is always equal to r cosine theta, and y is always equal to r sine theta. Tan of theta is always equal to y over x, and r squared always equals x squared plus y squared. So let's say r is equal to f of theta. Then x is equal to f of theta cosine theta, y is equal to f of theta sine theta. And then how do you differentiate it? dy dx is equal to f prime of theta sine theta plus f of theta cosine theta. And this is using the product rule, by the way, over f prime of theta cosine theta minus f of theta sine theta. So an easy way to just remember this is just y prime over x prime. So it'll be f theta sine theta over f theta cosine theta. I just solved it using the product rule for the two different functions, f of theta cosine theta and f of theta and sine theta. Okay, so how do you find the area of the polar regions? So essentially, here are the equations. So think of it as just the area is just the limit as n approaches infinity of 1/2 of the sum from I to n of f of I squared times the change in theta. This is pretty complicated, so you just have to memorize the second one really. Oh yeah, this first equation we went over in unit 6 too, by the way. It's just connecting limits to integrals. And the second equation is what you should probably remember. 1/2 times the integral from alpha to beta of r squared d theta. So the hard part is finding the correct alpha and beta to do the integral between. So essentially what you want to do is find when r equals 0, and then it'll most likely be the first possible angle when r equals 0 and the second possible angle. But just be sure to draw it on the diagram and make sure it makes sense what the two angles are. And yeah. Find when r equals 0, find the thetas that correspond to that from the equation, and yeah, find the correct alpha and beta. Okay, last topic, how do you find the area bounded by two polar curves? So it's the same equation as before, 1/2 times the 1/2 r squared d theta, the integral of that. So just look at the graph, find the angles that intersect, and determine which angles you want to do to set the integral from. And essentially, you have to be smart about it. Create different integrals, use symmetry to your advantage. And when you evaluate different integrals, see which curve is included in each integral. Yeah, so it's a circle bounded by a limacon or a cardioid curve. And essentially, those are the two intersection points. I circled them. And you want to find the intersection of that shaded area. So how do you do that? So the top part and the bottom part will be symmetric, so we'll only take the top part and then multiply by 2. The black region I've shaded, all of that is purely the circle. None of that area is coming from the limacon curve. That's purely the circle. And then the second half of the area, that's purely from the limacon curve. So we'll take the two integrals separately, one from the first two angles and the circle, and the second one from the second angle and the horizontal line from the limacon curve. We'll sum up both the integrals and then multiply by 2 to get the total one. And if you want to find the difference between two polar curves, you can use this equation. I drew a diagram on the left to show what I mean. I'll have two functions, f and g. Think of f as just a circle, and g is just that line. It'll just be the same thing. The integral f squared minus g squared, g theta, and 1/2 outside. And yeah, that's it for Unit 9. Unit 10, infinite sequences and series. Okay, first we need to understand what convergent and divergent infinite sums are. So convergent means that the sum of the infinite sum of a series, it'll converge to a certain value. This may seem hard to understand, but we'll go through it, and yeah, it'll make sense later. Divergent means it will not converge. It'll be infinity or negative infinity. So let's say there's this series. It goes from 1 to infinity of a of n. Then the sum of the whole thing is a1 plus a2 plus a3 all the way to an. If s of n converges, then that means that if s of n converges, that essentially just means that series converges. Otherwise, it'll diverge. That's just the notation for it, the thing I included on the left side. And on the right side, I have an example. let's say I want to find the infinite sum of 1 over 2n. Oh yeah, by the way, if it's a whole number, obviously it'll diverge, but for fractions, it's possible to converge. So here on the right side, I have a geometric series. Essentially, that just means you multiply by common ratio to get the series. So here you're multiplying by 1 over 2, basically. So essentially, the sum, it can just be thought of with 1 over 2 plus 1 over 2 squared plus 1 over 2 cubed dot all the way to 1 over 2 to the end. Then let's just multiply by 1/2 on both sides. Then we get 1/2 Sn, and Sn is the total sum from n equals 1 to n equals infinity. And then on the right side, since we multiplied the whole thing by 1/2, everything goes down by 1 power. Oh, I mean, everything goes up by 1 power. So just 1 over 2 squared plus 1 over 2 cubed all the way to 1 over 2 n plus 1. And now, what if we just subtract both of them? So we subtract s of n minus 1/2 s of n, and on the other side we subtract the top sum, 1 over 2 plus 1 over 2 squared all the way to 1 over 2 to the n. We do that minus 1 over 2 squared plus 1 over 2 cubed all the way to 1 over 2 to the n plus 1. Then what do we end up with? We end up with 1 over 2 s of n, and that's just equal to, since everything in the middle will cancel, the only thing that will not cancel is 1 over 2 minus 1 over 2 n plus 1. Then let's just multiply by 2 on both sides. Then we get s of n is equal to 1 minus 2 to the n. And here n is approaching infinity, so it's just 1 minus 0, and it's 1. So you can use this trick to try identifying if they'll converge or diverge, and we'll go over many other tricks in this unit as well. Okay, so I briefly mentioned it on the last slide, but a geometric series is a series where you start at a term A, and you're multiplying by a common ratio. So let's say I start at 3, and my ratio is 1. My ratio is 2. So the first term will be 3, the second term will be 6, third term will be 12, and so on. Then in a geometric series, if R, the ratio you're multiplying by, is greater than or equal to 1, it'll diverge. Otherwise, it converges. And the formula on what it converges to is AR to the power of K over 1 minus R. And K is just the starting term. So essentially, it's just the starting term over 1 minus R. That's what it'll converge to. All right, now I'm going to go over the nth term test. So if there's an infinite series, the infinite series will, and if it converges, that means the limit as n approaches infinity of the last term, a of n, will have to be equal to 0. If it converges, then that has to be true. If that statement is not true, if it's not equal to 0, then it diverges. But even if it is equal to 0, it's not fully confirmed that it converges yet. All you need to know is that if it converges, then it'll be true. The limit of a of n as n approaches infinity. So the last element, the infinity element, will be equal to 0. It'll approach 0 if it converges. So that means if it's not equal to 0, then it 100% diverges. But if it is equal to 0, it's not 100% confirmed that the series converges. Yeah. Okay, now I'm going to go over the integral test for convergence. So if f is positive, continuous, and decreasing, and by the way, for this one, it can technically, it can start off negative, and it can start off increasing, but at some point, everything else after that has to be decreasing, and everything else after that has to be positive to infinity. So if f is a function like that, and the limit and if the sum of the infinite series a of n and f of x, the integral from f of x both converge or diverge. Okay, yeah. So assuming, let's say a of n is equal to f of x. So we represent each term in the series as a function. That means the integral of f of x and the series will either both converge or diverge. This just logically makes sense. For an infinite series, if a function represents that each element in that series, then the integral of that function will just give the sum. So, or I mean, the integral of that function should be related to the sum. That's why they both will either converge or diverge together. And you can find out one and you can determine the other that way. Okay, P and harmonic series. So a P series is a series of the sum of 1 over n to the P. And then n can go from 1 to infinity. So it'll be 1 over 1 to the P, plus 1 over 2 to the P, plus 1 over 3 to the P, all the way to P equals infinity. So essentially here, it'll converge, the P series will converge if P is greater than 1, and it'll diverge if P is less than or equal to 1, and P still has to be greater than 0 regardless. Otherwise, if P is less than 0, then it's not going to be a pure P series anymore, because it'll just be 1 over 2 to the negative 1 is just 2. And a harmonic series is a special type of P series. So whenever P is equal to 1, that's the harmonic series. Okay, comparison test for divergence. Okay, so let's say there's a series A of n and a series B of n. If A of n is greater than 0, and B of n is always greater than or equal to A of n for every single n, then if the sum of all B of n converges, so if B of n converges, B of n converges, that means A of n also has to converge. This is because A of n is always less than or equal to B of n. It's just basic, think of the squeeze theorem. It's similar to that. If B of n converges and B is on top, then A of n also will have to converge. On the other hand, if A of n diverges and A of n is on the bottom, if A of n diverges, that means B of n will also have to diverge because B of n is on top of A of n. And A of n is never going to a value, it's always going to infinity. It's diverging. So B of n also has to diverge. Okay, so if A of n is greater than 0 and B of n is greater than 0, and if the limit at n approaching infinity of A of n over B of n is equal to a finite and positive value L, the limit of n equals 1 to infinity of A of n over B of n will both either converge or diverge. And yeah, so essentially all this is just the ratio test. If the ratio of A of n over B of n, the limit as n approaches infinity is a finite and positive constant, that means the sum of the series of both A of n and B of n, both of them will either converge together or both of them will either diverge together. So if you know one converges, then the other must converge too. If one diverges, the other must diverge too. Okay, alternating series test. If A of n is greater than 0, then the sum of n equals 1 to infinity of minus 1 to the power of n of A of n, and the sum of 1 to infinity of minus 1 n plus 1 A of n, both of them will converge if two things are met. One, if the limit of A of n as n approaches infinity equals 0, if that's true, and if A of n plus 1, if the next term is less than the current term for all n of A of n. And yeah, this is just the alternating series test for convergence. You can determine if two alternating series will converge or diverge using this test. Yeah. Okay, this is the ratio test for convergence. So if a series has only positive terms, then the limit of n approaching infinity of a of n plus 1. So they'll give you an equation, right? So the formula for the next term over the current term, the limit as n approaches infinity of that, if that's less than 1, it'll converge. Greater than 1, it'll diverge. And if it's equal to 1, then we can't conclude anything. So just use another test. Yeah, this is known as the ratio test. Earlier, I mentioned something else with the ratio test. I misspoke there. That's not the ratio test. This is the actual ratio test. Okay, absolute versus conditional convergence. So absolute convergence means that the absolute value of a series A of n, the absolute value of all terms converges, then the normal series will also converge. The sum of the infinite normal series will also converge if the absolute value of the series converges. Conditional convergence means that if the absolute value diverges, but the actual function converges, and divergent means that both diverge. So you can use this to your advantage to save time. For example, if you find out that the absolute value of a function a of n converges, then we 100% know that the actual function a of n will also converge. Yeah, that's an example. Okay, alternating series error bound. So we went over an alternating series just not too long ago. So if an alternating series converges, then the error bound S, the error bound, so essentially the S minus S of n is equal to R of n, and that's always going to be less than or equal to the next term of the function. So let's say an alternating series converges to a value S. That means the sum of all terms up to that point, S of n, the absolute value of the final thing it converges to, S minus S of n, that's equal to the R of n. We'll call it the remainder, R of n. And that's always going to be, for every n, that's always going to be less than or equal to the next actual term of the sequence. Let me repeat that again, just to make it clear. So an alternating series, let's say converges to a value S. And then the partial sum of the first n terms is S of n. Then for all n, the remainder, S minus S of n, the error, how much it's off by, the absolute value of that. Let's say that's equal to R of n, the remainder. And that's always going to be less than or equal to the next actual term of the series. So not the sum, the next actual term. And yeah, all these are an absolute value because they're all magnitude. Okay, Taylor polynomial approximations. So these are just approximations of a differentiable function f centered around an x equals c. And the coefficient of the nth degree term is just the n derivative of f of c over n factorial. So it's just an approximation. You can approximate the entire function by using derivatives around a certain point c. So that approximation will essentially be f of c plus f prime of c times by x minus c plus f double prime of c times by x minus c squared over 2 factorial all the way up to n factorial. So the n derivative of c, x minus c to the power of n over n factorial, and n is the order of approximation. So on the exam, you may be asked to do the third approximation or the fourth approximation. You just use this formula up to the third factorial or the fourth factorial or whatever. And yeah, just plug in the values. You might be asked to find a value, approximate a value x. So you'll plug in x there around a certain x equals c, and you'll plug in c there. Okay, Maclaurin polynomial approximation. These are just Taylor series, but they're approximate around x equals 0. It's the same formula, just replace all the c's with 0. So yeah, you just get this formula. All right, Lagrange error bound. So the error R of n for a Taylor approximation. So let's say f of x minus the Taylor approximation of the nth power of x, how much the Taylor approximation of the n power of f of x at the x value is off by, the absolute value of that. That's the remainder, and that's going to be less than or equal to the max. Okay, here you might get a bit confusing. The maximum of the n plus 1 derivative of f of some value z. So that it can be any value z between c and x. So for any value between there, you want to find the value that'll give you the max n plus 1 derivative of that. So you'll plug in the max y value, the max derivative value, the n plus 1 derivative value. You'll multiply that by x minus c to the power of n plus 1. And n is just the n derivative. And all of that over n plus 1 factorial. And all these are an absolute value. And yeah, that's the Lagrange error bound. It's a pretty powerful formula. As you can see, how much you're going to be off by. You can calculate what's the max amount you can be off by using a Taylor approximation. Okay, power series. So a power series is represented like this. The sum of a of n multiplied by x minus c to the power of n. And yeah, the sum of that. So let's start at n equals 0. That's just a of 0 plus a of 1, x minus c to the 1, plus a of 2, x minus c squared, and so on, plus all the way to a of n multiplied by x minus c to the power of n. Okay, so the domain is x values. So the domain of this function is only going to be x values where it converges. So for certain x values, this series will converge. And whatever those x values are, that's part of the domain. And what the power series is centered around, the x value is centered around c, it's always included. That means it's always going to converge at x equals c. So what are the radius and the interval of convergence of the power series? So a power series can converge in 3 ways. It can converge to an interval, it can converge to all real numbers, and it can converge to the center c only. So when it converges to an interval, the radius of that interval will be the absolute value of a minus c. A can either be the most left or rightmost point included in the range, and c is just the center value. And here's the ratio test for power series convergence. So let's set the value x to be equal to the limit as n approaches infinity of the absolute value of a n plus 1 over a of n. You'll again be given a function for this, so you'll just do a of n plus 1 over a of n, the absolute value of that, and find the limit as n approaches infinity. So that x value, the limit, if the x value is less than 1, it'll converge to an interval. If it's equal to 0, it'll converge to all x. But if it's equal to infinity, it'll converge just to the center c. And yeah, here's another thing you have to memorize. Okay, and here are some basic Maclaurin series for some functions that you may have to memorize, that you should memorize. First one, e to the x. So instead of solving it out, you can just memorize that it'll be equal to the sum of x to the n over n factorial of n equals 0 to infinity. Sine of x is minus 1 to the power of n multiplied by x to the 2n plus 1 over 2n plus 1 factorial. Cosine x is minus 1 to the power of n, x multiplied by x to the power of 2n over 2n factorial. 1 over 1 plus x is minus 1 to the power of n multiplied by x to the n. And the interval for convergence for the top 3 is just negative infinity, positive infinity. For the bottom one, it's negative 1, positive 1. So for these, you might get a problem like sine of x squared or x squared e to the x. For those, when that happens, you just replace every x value with, let's say it's x squared e to the x. You'll replace every x value with the function with the x plus 2. So here, x to the n over n factorial, you will replace that with x of n plus 2 over n factorial. For sine of x squared, you'll replace every x value with x plus 1. So here you'll replace, it'll be x to the power of 2n plus 2 instead for the sine of x. And yeah. So that's all of Unit 10 for AP Calc BC, and that's the entire curriculum. Of course, these are just concepts on the screen, but I truly recommend you all to practice the past FRQs which are publicly available, and practice lots of MCQ questions. Be sure you have a good understanding of all the topics and review if necessary. This last unit is pretty confusing, so you'll only truly understand it once you practice a lot. Thanks for listening. Let us know if you have any questions in the comments. And this video took a while to make. We'd greatly appreciate if you could subscribe